What if the next air conditioner was not a machine, but a layer of paint? In some labs, that idea is already real. The most advanced versions reflect almost all sunlight and send heat back toward space. Cities are becoming giant heat traps. Dark roofs can reach extreme temperatures on sunny afternoons, turning buildings into ovens. Then air conditioners fight the heat, consuming electricity and releasing even more hot air outside. IT is our loop, and this paint is designed to break it. The breakthrough came from a simple question: how white can white become? Researchers at Purdue University developed an ultra-white paint that reflects up to 98.1% of sunlight. That number sounds small until you realize ordinary white paint still absorbs enough energy to heat up. The secret is not magic. It is particle engineering. Inside the coating are tiny particles that scatter sunlight in many directions. Different particle sizes scatter different wavelengths, making the surface extremely reflective. But reflection is only half the story. The coating also emits thermal radiation through an atmospheric window where heat can escape into space. That is called passive radiative cooling. No pressure, no fan, no electricity. Purdue reported that a 1,000 square foot area could deliver about 10 kilowatts of cooling power under strong sun. That is more than the cooling power used by many home air conditioners. The paint does not make cold air like an AC system. It attacks the heat before it enters. That small difference changes everything. On homes, it can reduce roof temperature and cooling demand. On warehouses, it can protect workers and stored goods. On data centers, it could reduce the thermal stress around machines that already run hot. On trucks and refrigerated containers, it could slow heat gain during long transport. On fuel tanks, it could help less overheating. And on city rooftops, it could fight the urban heat island effect one surface at a time. But this technology has a weakness. Dirt can reduce reflectivity. Rain, pollution, aging, and abrasion can change performance over time. Climate matters too. A coating that works brilliantly in a hot, dry city may perform differently under humid skies. There is also a winter question. In cold regions, reflecting sunlight can sometimes remove useful heat. So the future is not one paint for every roof. It is smart deployment. The reason this matters is simple. Cooling is becoming one of the biggest energy challenges of the century. Billions of people live in places where heat is not just uncomfortable, but dangerous. Air conditioning helps, but it is expensive, energy-hungry, and unequal. Paint is different. IT is familiar, IT is scalable, and it does not require people to understand quantum physics to use it. Now engineers are racing to make these coatings thinner, tougher, cheaper, and easier to manufacture. The challenge is brutal. A roof coating must survive years of sunlight, storms, dust, and temperature swings. It must stay bright without becoming fragile. It must reflect light without blinding people. It must cool without creating new environmental problems. That is why the story is not only about whiteness. It is about durability, chemistry, cost, and trust. The next generation may not even look pure white. Researchers are exploring materials that reflect infrared heat while keeping visible colors architects actually want. That could bring cooling paint from industrial roofs into homes, schools, hospitals, and public spaces. Imagine a heat wave where the city does not simply endure the sun. IT jacks IT. That is the real promise. Not a miracle coating, a passive shield against a hotter world. The strange part is that this solution looks almost too ordinary. Or brush. Ola. A surface that refuses to absorb the day. For centuries, people painted buildings white because it helped with heat. Now science is turning that ancient instinct into engineered climate technology. The question is no longer whether paint can cool. The question is how far we can scale it before the next heat wave arrives. Because sometimes the most disruptive invention is not the one that makes noise. It is the one that silently changes the temperature of everything around it. And if the hottest cities on Earth begin to wear this new skin, the skyline itself could become a cooling machine. No engines, no fuel, just sunlight, chemistry, and one of the oldest materials humans ever trusted. The future of cooling may already be drying on a roof.